you so much. Well, thank you so much. Thank you. Really appreciate it. Hello, everyone, and thank you so much for being here. Today, I wanted to talk about scaling AI ML workflows on HPC, specifically for geoscientific applications, and the challenges and opportunities that are in this space. And this is a work that I've done with a list of colleagues. It's not myself only. So I just wanted to acknowledge all of their contributions as well. Okay, a quick intro about myself. Similar to many others here, I actually started as an atmospheric scientist, and then I became interested more towards like the computational side of our domain and software engineering side, and moved more towards that direction. So today at NCAR, I help building infrastructure for AI/ML for climate and weather modeling. And I've been helping with the Pangeo community as well, try to port codes to GPUs and a bunch more. So, and that's my contact information. Okay, so today I wanted to talk about distributed training for geospatial workflows, parallelization paradigms in PyTorch, and what are the methods essentially for distributed training, and optimizing distributed training and single node training, and what areas of optimization exists. Okay, so if we look at a typical AI/ML workflow in geosciences, it starts with data. So we have like either ZAR, NetCDF, HDF. We have a lot of fantastic talks and posters this week about all these different packages. There is a component of data ingestion and pre-processing that happens using Xarray, Dask, and some folks use CuPy for GPU native pre-processing. And then the training and validation using JAX, PyTorch. I don't personally like TensorFlow. I don't think TensorFlow should be used, but yeah, some people like TensorFlow as well. And then all of this result in a trained model. And then the next step, folks use the trained model to run inference and interact with essentially the model in inference mode. As it turns out, GPUs are really good in matrix multiplications, and the training part, the AI training part, and the inference part happens on the GPUs. And these models essentially are like diffusion models, UNets, and that type of models that are becoming very, very popular these days in the geosciences fields. So why distributed training? Because we used to do this actually, like during my postdoc years in 2017, 2018, I was doing AI/ML and I was using single GPUs and almost similar, very similar workflows. So why do we need distributed training now? I like to say big AI is here for geosciences. So distributed training, it means a training paradigm that involves spreading your models or your workload across different units, GPUs, TPUs. And we need distributed training because we have more and more data. We have like more satellite data, more sensor data, more model data. And we have we are trying to train large models. So I added like some stats on some of these big models like that are very famous in the geosciences and weather modeling. And the GraphCast that came out 2023 had like around 40 million parameters. NCAR VaxFormer had around 420 parameters. And Aurora that came out this year, it had like around 1 billion parameters. And this image is essentially from the numerical models back then, and the point of this image is that we were going towards more and more high-resolution models and more ensembles, and we generate more data. And I think the same is true now with the AI models, and we are doing like more like high-resolution models. So what is the issue here? So I don't know how many of you have seen the runtime error, the CUDA out-of-memory error. Yeah, that's a very frustrating one, I have to say. So technically, you want like bigger batches and more layers. You want bigger batches so that you can train easily, but the bigger batches usually like lead to the runtime error, the CUDA out of memory. And to understand like what goes on to the VRAM or the memory of the GPU, there are like the parameters, the gradients, and the optimizer state usually goes on the VRAM. This is Atom optimizer, but it can be like other optimizers as well. And the more and the bigger the batches, like the more data essentially like you're storing on your VRAM. This is an image of a fancy A100. So the A100s, they have there are two flavors of them, for 40 gig and 80 gig. And the H100s, for example, they have like around the 80 VRAM. The ones that we have, like usually the ones that folks use for like gaming or like they have at home, the 5090, which is like the most advanced, the recent luxury ones, like a 32 gigabyte of VRAM, which is like something that we couldn't even imagine like a few years ago. Okay, at NCAR we have like two big machines. We have the Ratio, which has a lot of GPUs on each of the nodes. It technically has like 4 GPUs on each of the nodes, and users can use it for like training large models. These GPUs are the A100, the 40 gigs. And we have also another machine called Casper, and Casper it doesn't have a nice banner, so you can see inside of Casper. And on Casper, user can request for a single GPU, and it has a lot of different GPU types, A100s, H100s. And they can use it for running inference, or they can use it for running training workflows. Okay, so with this quick intro on like the distributed training paradigms, so there are like two different ways of parallelizing your workflow so that you don't hit that or the out of memory. There is the data parallelism, so essentially you shard your data between the different workers and between the different GPUs. And the other one is model parallelism. So when your model doesn't fit inside the VRAM of the GPU, you shard your model and give like a piece of your model to one of the GPUs, and the GPU trains on that, like essentially like that piece of the model. And distributed training in PyTorch specifically, there are two famous methods or two well-known methods, DDP or distributed data parallel, and FSDP, fully sharded data parallel. Both of them work for multi-node, multi-GPU. I'm going to skip this slide. I hope that you know the basic training loop in PyTorch, like a forward pass, loss calculation, backward pass, and optimizer state. In DDP, what happens, and this is a perfect image kind of like to explain it, you shard your data and send it to the different GPUs. And you can see this is for LLMs, but these are like not LLMs technically. But you shard your data and send it to the different GPUs. It does the forward pass and backward pass, and then in this step, it needs to synchronize. Otherwise, the training, it's as if like we are training the same model on 4 different GPUs. We are not like distributing it. So we need that all reduce, that synchronized step. And DDP is like very easy to implement. I really like DDP myself. It's very scalable. It has a high memory usage. Right now, the geosciences, weather and climate, we haven't hit that like very big trillions of parameters threshold that like essentially like LLMs are in. We are like around like millions and billions. But yeah, so models still fit on like a GPU, on a single GPU, and DDP can be a good choice for them. So if the model doesn't fit on a single GPU, FSDP is a really good paradigm or model for essentially distribute your training. So FSDP is very memory efficient, but it has a lot more communication overhead because of the communications that happens between the GPUs. You can see both the model and the data is now sharded, and we need to do a lot more communications in each step to make sure that we are in sync. The fully sharded data parallel, it has a lot of different knobs to reduce the memory footprint, and that's the goal of it. It tries to help you to fit your model state onto a single VRAM of your GPU. So you can like shard your model differently, you can do checkpointing, and then there are other methods of like precision policy, gradient accumulation that's technically can be used for other paradigms as well. But yeah, these also help with reducing the memory footprints. For us at NCAR, I mentioned we have the A100s to the 40 gig A100s, and that those have a smaller VRAM. So we see a lot of our scientists are more interested in the FSDP because of that. Otherwise, like with the 80 gigabyte of memory, DDP works absolutely fine, and you can use it for training. And this is essentially like a summary of what I mentioned. The communication overhead is much higher on FSDP, but it's like an ideal, very ideal for like models that are like essentially like larger, or when we have like smaller VRAMs, for example, us. And DDP is like simpler to set up. So it all depends on the hardware you have access to and the model you are trying to train. Okay, so you see, PyTorch makes scaling easy and fast, and that's what we joke about all the time, because it doesn't. No, it doesn't. Scaling with PyTorch is not easy and fast, and I can explain why. We have a lot of like scientists and users that are interested in scaling their models on their HO, and they don't know where to start. We try to provide a template for them. And the NCAR credit is essentially like the scalable platform and a lot more, but for training and inference of the AI, weather, and Earth system models. It came from a template of a PBS job, very similar to a Dask job queue that John Schreck and I worked on like 2023, but then it grew and became more, so it has like now a lot more support for a lot more of the functionalities. And Charlie here will talk about credit a lot more in the next talk. Okay, so this is all great. We know how to scale on HPC. We know how to do PyTorch, okay? But you said it's going to be fast, and I don't see it becoming fast. So what is the problem? So if I explain everything in a good way so far, you should have known that there are two big bottlenecks in all these workflows. One is data loading, the other one is the synchronization step. Otherwise, the GPUs are very, very fast. And that's a trend that we see with a lot of different scientists' workflows, that they have like their GPUs idle and they're not doing real workloads on the GPUs. So I'll talk about like how to resolve those next. So the first one, the communication overhead, and this is just a makeshift timeline of the host device for a single GPU training. So you can see like this is the data loading, and the device like this is training, and then here we have the GPU idle or the device idle, and that's bad. We don't want this. In the distributed training, we have the syncing step as well, the synchronization step that also like it requires a lot of time, and it becomes a bottleneck, and it causes the GPUs to become idle, and that's bad as well. So next I'm going to talk about the communication overhead and like how we resolve it. So there are different libraries or different backends essentially for communication that's supported by Torch. Gloo, MPI, and Nickel. So Gloo is a CPU-based one. It's very good for CPU-based communication, not good at all for GPU-based, and we are doing GPU-based, so yeah, that doesn't work. MPI is really good, and it's reliable, it's versatile, but yeah, it doesn't have as good as the performance of Nickel. Nickel is NCAR, NVIDIA collective communication library, and it's an optimized library for communication on the GPUs. And this is essentially like a snapshot of the Insight system, and showing that if Nickel is not set correctly, a lot of time is spent on Nickel. Although Nickel is optimized, it's very, very important to make sure that you have set it up correctly. Otherwise, you have to spend a lot of time on communication with Nickel. And on Ratio, we have like these nodes that have like 4 GPUs per node, and these GPUs are connected with NVLink, and they are like doing communications very fast. But beyond that one node, when we want to do communication with the next node, now we have to rely on the slingshot, essentially the lib fabric that we have under HO, and it's the same for cloud as well. The cloud providers also like struggle with the same thing. So there are like different plugins for Nickel to make it more performant, and one of them is the AWS O5 Nickel plugin. It's essentially like a communication plugin for NVIDIA Nickel and the fabric, and to make sure that they work nicely. And the Nickel library is using the slingshot, for example, that we are using at NCAR, or like the lib fabric, essentially, to have like that high level of communication. And this is some benchmarking results of like the different backends. So you can see like for 8 GPUs, this is 2 nodes, Gloo, MPI, nickel, and the nickel optimized. And this is just a bunch of like different environment variables for optimizing nickel. And this is just speed. So you can see like how much faster, because it's log scale, how much faster is nickel on big tensor when we are like moving big tensors like between the GPUs. MPI is actually surprisingly good in smaller tensor packages when we send those smaller tensor packages, or when we are scaling up to many, many nodes. And MPI should be, I think, considered for a lot of people because it's easier to set up as well. Gloo is really bad, and when nickel is not set up correctly, it's kind of like falls to the similar performance as like the TCP IP, so it's like not going to be good performance. You can see like this is on log scale, so it's a very big difference between the communications. But the big difficulty here is that building an MPI compliant PyTorch with nickel is very, very difficult. So at NCAR, we have created this framework for building PyTorch with MPI and nickel. But yeah, this is a pain point for a lot of people. So, and also it's a bigger challenge on the cloud as well. The cloud providers struggle with the same thing. This is, for example, the result of benchmarking another application. So you can see like how much more time, this is just time per epoch, so how much more time is spent on with the Gloo backend, with CPU to CPU communication versus the GPU to GPU. The nickel one and the MPI one. So when in doubt, actually, if you use MPI, it's going to be more performant than the not correctly set up nickel library. So that's an important point to take home about this part. I kind of wanted to go over like all these bottlenecks and how they can degrade the performance. If there's a mismatch, should rely on the CUDA aware MPI. If there are like any mismatches, there would be inefficient collectives, and that's not good. We don't want that. And that's this part. So if you are interested in the networking and these like different essentially backends, come talk to me after this talk. I also wanted to talk about I/O, and I/O is another big bottleneck in a lot of our workflows. And again, like this is just a schematic of it. If we reduce this, now I/O and the loading of data becomes very big bottleneck in our workflows. And that's true for both single GPU and multi-GPU training. Also for inference workflows, I/O is a big bottleneck. So with a group of people during actually a hackathon, it was a 3-day, 4-day hackathon. We set aside some time to kind of better understand the GPU native workflows that exist. What kind of improvements can we make to the AI/ML throughput using these GPU native workflows, especially like ZAR, MVComp, QuickIO, and like try to put together an example of ZAR and DALI together and understand like how chunking cause like performance degradations. And I really like this flow chart because it kind of shows the flow of data. So we have like a data on the like some sort of storage, and then we read it to CPU. So for example, we have ZAR, and then using XRE, we read it to our CPU, and then it has to transfer over the PCIe switch and to the GPU, and now the training happens here. So if we have like essentially a workflow that bypasses this part, it's going to be much faster. We don't have to copy everything over to the CPU and then again to the GPU. So we're going to be much better. For this, we put together a benchmark of a unit, just like training on a set of like arrow 5 surface variables. Again, a benchmark, so we wanted to understand like what are the pain points and how we can improve them. One thing that we realized very, very fast and very soon was that chunking to match access pattern is one of the important things for improving the performance and the throughput of our AI/ML workflows. So here you can see like 1 GPU, 4 GPU, 8 GPUs, and 16 GPUs, so essentially like different number of nodes. And you can see how the baseline that didn't match, the chunking on it didn't match the access pattern was having a really bad performance compared to when we rechunked the data to match the access pattern, and it had like almost 2x like performance improvement. This was a very easy fix, and I think something that all of you, if you are doing this type of work, you should be mindful about. Compression was another interesting part as well. So you can see when we were like doing 1 GPU or 4 GPU, the uncompressed ZAR actually was showing better performance. But when we scaled it up, and this was because this like on 1 GPU or 4 GPUs was more CPU bound, and then when we were like trying to read a lot more data, it became IO bound. Yeah, so the performance became worse. So compressed ZAR is good, but we should make sure that it's chunked to match the access pattern. Okay, thank you. GPU native ZAR, ZAR v3 has been released recently in January, and it had almost fully GPU native support. So we started like essentially like trying with that. Right now, almost all the pieces are there except for the decompression using MVComp, and that piece is still a PR. We did some testing with that, and we showed that the Z-standard decompression on GPUs when we use MVComp is at least like 30% faster. If you're interested about this, I'd be happy to discuss this. We have also write a blog post about this. Overall, we did like a bunch of different strategies. We put together an NVIDIA DALI workflow example, essentially, and we tried to do a lot more optimizations that we explained in that blog post, and all of that resulted in around like 17x speed up on the training work, like throughput on a single GPU, and similar results also for multi-GPUs. And also we learned a ton. One of the most important things for me was always using NVIDIA Insight for profiling, and the MVTX marker. I'm not good in using MVTX markers, but like those would be very helpful for identifying if it's a nickel issue, if it's not a nickel issue. And if you are interested, this blog post just came out actually today, so please feel free to check it out. It has a lot more information on XRA, ZAR, DALI, and how we improved the whole end-to-end workflow. So yeah, if I wanted to have like a summary of everything that we discussed today, I want to mention first, scaling the AI training is very, very difficult, and it's not very efficient for scientists and domain scientists. We definitely need more GPU native packages and scalable platforms to make it easier for scientists and more efficient. We can learn a lot from the computer vision and the LLM communities. How do they like do these? How to make it easier for scaling their workflows? Data loading is still a major bottleneck for both single GPU and multi-GPU training. Communication is also another bottleneck for the multi-GPU training. Both of these can be improved, so there are ways to improve these. But there are some also opportunities. So chunking based on the access pattern matters a lot. How do we want to serve the community and build like smart chunking workflows to help with like different access patterns? So for example, the climatology would be like a very different access pattern versus someone that's interested in only a region of the data set. So how do we want to chunk the data and serve it in a way that's more efficient for everyone? We've been thinking about AI-ready data for the past 5 years or so, but maybe we should think more about AI-ready data pipelines. So that might be another focus area. And so far, I just talked about PyTorch, but JAX also is another framework for, and you can use it for distributed training. And we haven't talked about JAX at all. We need more GPU native packages and pipelines, and there are a lot of work happening. GeoTIFF to GPUs is like being developed by Wei Jiliang, DevSeed. ZAR XRA to JAX is also like another workflow that's being explored. So we need to think about all these, and there are several opportunities in this space that we can talk more about. And this is just a snapshot of the PanGeoML community, the PanGeoML packages from 2023. We need to think about how it would look like in the upcoming years. I just added ice chunk there as well, because that's new. Well, thank you so much, everyone, for listening to me for the past 30 minutes. I'd be happy to chat with all of you about like next steps, if you have any ideas, or if you think that there are like possibilities for any areas to fix like the workflow. Yeah. So thank you so much.
All right, so thank you once again, Negin. We've got a couple of minutes for questions, if anyone has. So great, I'll just bring the microphone over. If you wouldn't mind just introducing yourself, that'd be great.
Oh, sure. Hey, I'm Seb, an AI engineer. Thanks for the presentation, that was pretty awesome. Recently, I worked quite a bit with Cerebras. They created a wafer that is, I think, 60 times, 56 times bigger than a normal GPU. Have you read about any studies where people do scientific simulations on those chips or like groks?
I have seen the news about those chips, but I have not seen at least like anyone in our community doing like simulations on those chips. But yeah, I'd be actually interested to see like what it would.
Yeah, I met them at a conference in Vancouver last year. Every chip is $1 million, so I guess it's a little bit hard to get to them.
Yes.
But yeah, it would be really interesting to see like if those bottlenecks actually could be prevented.
Yeah.
Thanks.
And I've heard that there is like a delay on like delivering those as well. So
I bet.
yeah, I bet that there is a delay. So.
Thank you, and we have a great question from Olivia, who's here, I think. Can you speak a bit more about AI-ready data pipelines, maybe examples of, or what your perspective is on the need behind them?
Yeah, that's a great, fantastic question. So AI-ready data pipelines for me is more than like just the data. It would be like how the data is loaded to the GPUs, how we are just loading the part of the data that we need. We are not loading any extra data because like these are very fast workflows. These are very fast workflows and we don't want to load a bunch more data to it. Ice Chunk obviously like is being developed and it's also has a lot of potential. There are different ways to think about AI-ready data pipelines, but that's not being discussed much overall. Like we were mostly like focused on the AI-ready data. I think there are some opportunities in the AI-ready data pipelines to serve the data directly from the storage, like cloud, like local, wherever, to like your GPUs or the chip that you want to do training on.